Okay. We are going to go ahead and get started. Daphne, if you don't mind watching the wait room for me. Hello, everyone, and welcome to LLRISE. My name is Chiamaka Porter, and I help manage the K-12 STEM outreach efforts for MIT Lincoln Laboratory. Before we get started, I want to make sure that you're aware that today's presentations are being recorded. And to also please make sure you're muted at all times unless you have a question towards the end of the presentation. And in terms of questions, please hold all questions to the end of each presentation. You can type your question in the chat or use the raise hand function at the bottom of your screen. Okay, now that we've gotten all of that out of the way, so we have gathered here today in this virtual platform to celebrate the final presentation for this year's LLRISE class. LLRISE held its first session in 2012. It started out with only 12 students from Massachusetts. And today we have 31 amazing students from across the country. We developed LLRISE to inspire and motivate young minds to consider majoring in a STEM field. We also encourage students to showcase their talents and realize their potential, and to see that it doesn't matter where you come from. If you put in the hard work and accept failures and learn from them, they can achieve anything they put their minds to. Today, we want to celebrate the success of our LLRISE students and give them a chance to highlight some of these successes that I am so proud for, as they worked very hard these past 2 weeks on college level information given to them by our Lincoln instructors. So with that being said, we are going to start the presentation. And our first group, let's start sharing our screen.
All right. Hello, everyone. We are Team Lambda Sauce, and this is the final presentation for all of our LLRISE experiments. Our group members are Sujay Champati, Emma Chen, Vicky Fernandez, Archer Liu, Hayden Ranshaw, and Dea Jupi.
Well, hello, everyone. Before we get started, we wanted to give a quick overview on what we will be talking about today in our presentation. Today, we will be discussing our problem statement, talking about the purpose behind our project, a little bit of history and background on radars, and of course, diving into the experiments themselves and the results. For our project, we worked with SAR, range, and Doppler, which we will go more in depth on later, and we will be ending with a quick summary of our experience here and acknowledging those who helped us get to this point. So during this program, we used a small laptop-based radar to collect data as well as analyze it. With our radars, we conducted experiments which tested the radars in 3 different modes: Doppler, range, and SAR. Each of these modes had a specific form of data that they collected, which included speed, distance, and spatial orientation. We will be talking a little bit about the history and background of radar for those who may need a recap or don't have much knowledge on this topic. Radars bloomed in popularity during the 1930s with their involvement in the military. And you can see here, there's a picture of a World War II radar, but however now they are constantly evolving and are widely used in a range of applications.
How does a radar work? So basically, a radar works by emitting waves from its antenna. Many of you have probably seen big radars with antennas on top of hills or mountains nearby where you live. These waves are emitted through space. They strike a certain target and then are reflected back towards the radar. The radar is able to detect these waves, and through several hardware components is able to convert those waves into a signal, which is then processed by computer programs to create a plot or a graph that we as scientists can then interpret. The data that's produced can include how far away the object is, how fast the object is going, and what the object looks like. So for example, a military radar could detect an enemy plane. It could know its coordinates, what type of plane it is, and how fast it goes just by firing waves at it. And finally, these waves are electromagnetic waves, which basically means that they're traveling at the speed of light, or approximately 300 million meters per second. So we get almost instant data on position and velocity from the radar.
So over here is the radar that we as students are using. The picture at the upper right is where it sends and receives the signals. And the picture at the upper left is what the radar looks like in general. And at the bottom is the software settings of the GUI, which can be all adjusted to optimize the best results for the 3 types of experiments that we're going to conduct. Next slide, please.
The following experiments use SAR, or synthetic aperture radar. This technique involves taking multiple scans of a scene while moving the radar along a second dimension. By comparing how the distance to each target changes over successive scans, we're able to generate a 2D image similar to a bird's eye view of the scene. Next slide, please. We wanted to see how far our radar could reach, so we went to a park to scan this scene. We set the radar in the bleachers shown in the bottom left and aimed it towards the tennis courts. As you can see, the y-axis is the distance from the radar, so we move the radar along the x-axis. As the field is mostly empty, the radar will most strongly detect the fences around the baseball field and the tennis courts, as well as the trees on the left. Next slide, please. Here you can see the plot generated by the radar. Both axes represent distance, so this plot is essentially a top view of the park. As you can see, the radar was able to achieve a very impressive range of over 100 meters. The scale on the right indicates the signal strength, with dark blue being an area of no signal return and dark red being an area of very strong signal return. Because the metal fences are very reflective, the radar received the strongest return signal from them, with light blue markings indicating trees, people, and other slightly reflective objects. Next slide, please. This is an overhead view of the park with the location of our radar circled. When we add an overlay of our SAR data, we can see that the generated image lines up nicely with the main features of the park.
In this next experiment, we wanted to test what features the radar could detect, but this time on a smaller scale, here in a living room. On the left, you can see our setup. On top of the table is the radar and the ruler that the radar was moved along. On the right, you can see the living room. And so just to get a sense of scale, the table in the back is 5 meters away. We performed 2 experiments, one with the living room and then another one with an exercise ball 3 meters away. So here you can see the data recorded by the radar. So the x-axis shows the distance running parallel to the radar, and the y-axis shows the distance straight ahead from the radar. So in each of the readings, you can see a dark red spot in the middle, which is the table that was 5 meters away from the radar, which shows that the reading is pretty accurate, as the y-axis reads this table as between 5 and 7 meters away. The plot on the left is the experiment without the ball, and you can see that between the radar and the table, nothing was detected. But in the experiment with the ball on the right, you can see that the ball was detected and there was a red spot there. So here is an image of the room layered with the radar data. You can see that the main features of the room were detected, such as the table in the back, the couch on the left, the TV on the right, and the small rocking chair on the right. Oh, okay. So now in our next 2 experiments, we will use the ranging mode of the radar. So the way that ranging works is that it uses the time that the emitted signal takes to return to the radar to calculate the distance away. And we also use a technique called moving target indication to eliminate the noise from the surroundings, so we could focus in on only the moving target.
So for our first ranging experiment, we wrapped an exercise ball in tinfoil, as you can see in the images. And the tinfoil is reflective enough for the radar to get good reading on the object. And on the picture to the right, you could see that the ball is rolled down the stairs, and then the radar is going to read how far the ball is from the radar itself. And if you go to the next slide, you can see the graph produced by the radar. The x-axis represents the range, which is how far the object is from the radar in meters, and the y-axis is the time elapsed. Then there's also the red spots, which each one represents when the ball bounced. And you can see as time goes on, the ball goes further and further away until it bounces from the wall at around 6 seconds. Then it bounces up the stairs, and then gravity pulls it back down again. And then something similar could be seen at the graph to the right.
Hi, I'm Hayden, and for our next experiment, we use the ranging from a radar to track a moving target, which is a person, and a projectile, in this case a ball, colliding with them. So we wanted to see whether or not we could determine which target the ball hit solely based on our radar data. And so even though this experiment was just a ball being thrown to a person, the same principles and radar techniques can be used for other applications, such as for tracking missiles and their collisions with targets.
Here you can see our setup for the experiment. We have our radar setup over here connected to our computer, which displays the data. There are two people moving back and forth at different ranges, and the ball is thrown, and we hope that the radar will be able to detect all three objects as distinct.
So for the data for our first trial, on the next slide here, it shows one target colliding with one projectile, in our case, a person catching a ball while moving. So this data is taken by the radar as thin strips that scroll up the page, and it forms this waterfall graph, with the y-axis being time and the x-axis being the range from the radar. So because of this, you can see the target moving away from the radar at about 0 meters at 7 seconds, to 6 meters at 16 seconds, and then back to 0 meters at 24 seconds. It shows in the data as a diagonal, but really it's just the person moving straight back and straight forward. And so you can also see the projectile is just a thin line, and that's because it's moving much quicker than the person. And so it takes up a much smaller area on the graph. You can see the projectile collide with the target's path right here at about 15 seconds, about 5 meters from the radar. So for our next trial, we have two targets moving back and forth. And in this trial, you'll see target 1 being hit by the projectile. And since the line doesn't continue through, we can tell that it stopped at target 1 and collided with it. And this collision is just before the 28-second mark at about 4 meters from the radar. It's this orange streak. In our next trial, we showed target 2 being hit. And target 2 is actually hit twice. And once here at 12 seconds, and then once at 21 seconds. So since we can distinguish between which targets being hit between the previous trial and this trial, this has a lot of application to the real world, since we can decide which target a projectile has hit. The second one at 21 seconds is a little bit harder to see because it's traveling through the target, but you can clearly see from this arrow a distinct orange streak.
Okay, so the third and final mode of our radar is the Doppler mode. The Doppler radar is used to measure the speed of different objects using a phenomenon known as the Doppler effect, where waves emitted by objects moving towards you are kind of compressed, resulting in a higher frequency. If someone was towards the left of this car, then they would detect sound waves, in this case, that are compressed at a higher frequency. If they were towards the right, it would be the opposite. They would detect sound waves that are at a lower frequency and stretched out. And basically, the radar is going to determine the velocity the target is going at by measuring this change in frequency. For example, if the frequency is higher than what the radar emitted, then the radar can tell that the car is moving towards it, and we as the scientists can then interpret that data.
So for our first Doppler experiment, our group wanted to test what really is the world's fastest paper airplane. So in the next slide, after some research, we discovered that 2 sources claim to have the world's fastest paper airplane, but of course, that title can only be claimed by one. The 2 sources that claimed this was the Origami Tutorial and Pinstripe magazine. So our group had recreated those paper airplanes and put them to the test. In the next slide, you can see that first up was the origami plane. Here in the photo, you can see that only a part of the plane is wrapped in tinfoil. However, when we performed the experiments, the whole plane was made of tinfoil to get a better reading. However, for visual purposes, we included this photo so you would be able to see the design and shape more clearly. And after performing our trials, we calculated that the origami plane had an average speed of 8.14 meters per second. This can be depicted on the graph where you see this peak. On the x-axis is the range rate, which is in meters per second, and this peak shows the point at which the paper airplane crossed over the radar, representing its speed. Now remember, the origami plane had an average speed of 8.14 meters per second. And keep that in mind as we go on to the next slide. So now moving on to the pinstripe plane. Again, the plane used in the experiments was completely wrapped in tinfoil, but we provided this image to better show the shape of the plane and the design that we used. After performing our experiments, we calculated that there was an average speed for the pinstripe plane to be 8.76 meters per second. Again, this is depicted on the graph by the peak. And in the next slide, with these calculations in mind, the title of the world's fastest paper airplane is awarded to the Pinstripe magazine, with their paper airplane having an average of 8.76 meters per second, which is an astonishing 20 miles per hour if you were to convert it. So congratulations, Pinstripe.
Okay, and so our final project, and one of the hardest to do for sure, is related to swimming. Essentially, we wanted to track a person's kicking speed through the water. So that means I hold on to something using no arms and use only legs. So we used 3 different types of swimming kicks, a breaststroke kick, a freestyle kick, and a dolphin kick to determine which one was the fastest. But additionally, we wanted to determine the nature of each kick. So what is the maximum speed? How long is that speed held for? And what is the distribution of speed over time? Over here, you can see the setup with a computer on a chair over here connected to the radar. The radar is pointing towards a person with a tinfoil hat strapped to their head, kicking through the water. The tinfoil is used for increased reflectivity, so we get a stronger signal. So the first kick that we have over here is the freestyle kick. We have the x-axis, which is my speed in meters per second, and the y-axis is time in seconds. So the bottom is 0 and time increases as you go up. As you can see in the graph to the top right, in the GIF to the top right, the freestyle kick is relatively uniform and continuous, so we have constant propulsion throughout the kick. This is reflected in this portion of the graph. Starting at about 4 seconds is where we reach this relatively constant speed until 8.5 meters per second. So across this time interval, we see that the constant speed is about 1.5 meters per second. That's the average speed. And the top speed is only slightly higher than that average at 1.6 meters per second. Now, again, the further out these bars go, the faster I'm going. So all of you may be wondering why there's this massive spike at the bottom near 1.6 seconds. So initially, we thought that was just a disturbance in the radar, extraneous noise that we could ignore. But after, we realized that it's actually the person's speed pushing off of the wall. As you can see, the spike is really narrow, which is reflected in the pool, because as soon as you push off the wall, there's increased resistance from the water, so your velocity goes down and increases again when the person starts kicking. So the speed is lost off the wall pretty quickly. In the second graph, the axes are again the same. And looking at the GIF, you can see that the breaststroke kick is very different than the freestyle, because per cycle, there's only one main point of propulsion. And that is actually the reason why you can see these spikes over here. At approximately 3 seconds, the velocity of the person increases rapidly because they kicked. And then between cycles, it drops off significantly, increases again after a kick, and so on. So there were about 8 kicks between 3 seconds and 8 seconds. And the top speed of this breaststroke kick is actually faster than that of the freestyle kick, but that speed is lost very quickly because there's very little propulsion. Then I get another spike, so I'm not able to sustain that speed for as long as I did the freestyle kick. And the final kick that we did was the dolphin kick. And here there are 2 main points of propulsion for each stroke. So again, you can see that in these twin spikes over here. So let's take the spike at 5 seconds. I started my cycle. I have a point of propulsion, drops off slightly, and then again comes up for the second kick in the cycle, drops all the way back down at 6 seconds where I'm in the middle of cycles. So I gain lots of velocity. That velocity drops off a bit and then gain it again. So the top speed here is 1.85 meters per second. And as you can see, based on the previous 2 graphs, the breaststroke had the greatest maximum speed, but it could not be sustained as long as the dolphin kick and the freestyle kick. And this experiment really shows how amazing a radar can be, because someone can actually use these graphs to determine which stroke the person was swimming without actually observing the person. And this is what radars are used for in real life. We can actually determine what is happening using the physics and math of radar systems without observing what's actually happening with our 5 senses. So a sixth sense, in a sense.
Over the past 2 weeks, we used our radar to map our surroundings, track the range of moving objects, and measure speed using the Doppler effect. Although it took a lot of trial and error, we learned how to efficiently collect and analyze radar data and conducted experiments related to real-life situations.
So we'd like to thank Dr. Eric Evans, the director of the Lincoln Laboratory, Mr. Louis Lopez, the director of the Department of Defense STEM, Chiamaka and Daphne, also our TAs, Theanan and Jack, all of our lecturers, everyone who helped with our experiments, and everyone who's here today. Thank you for listening, and are there any questions?
So if you have a question, please raise your hand and we will call on you. Or you can type in the chat as well if you're shy, camera shy. Somebody has to ask a question. I can't let them go without at least one question.
Leah asked, what was your favorite experiment?
Well, since
Sorry,
we all
go
did
ahead.
different experiments, so I think we all have a little bit of a biased opinion. I like the paper airplane one the most, since that was one I did, but I know Sujay has his own.
My favorite was definitely the swimming, because it relates to something that I'm really interested in and I do for fun, which is swimming. And also I was able to, before I did the actual swimming, I was able to, I just thought about what is my radar shape going to, what is the shape of my graph going to look like? And then when I actually did the experiment, it was really cool that the graph that I got was actually like what I was thinking in my head. Okay, there's actually a lot of questions in the chat now. So, can someone read the questions?
And I saw another question in the chat that said, can you explain the difference in the amount of trials for the pinstripe plane and the origami plane? So if you had a keen eye, you might have noticed that there was 9 trials for our origami plane, but only 7 for the pinstripe plane. And that was because we actually took 10 trials in total for both planes, or not in total, 10 trials for each plane. But then some of them were unreadable or were difficult to read, and I didn't really trust the data had skewed that much. So I took the 7 best for the pinstripe and the 9 best for the origami plane.
Okay, there's another question that says, for the swimming Doppler experiment, was the radar on the side or in front? So it was in front. So I was swimming towards, or I was kicking towards the radar. So that answered another question who asked who did the swimming. What was the most interesting thing you learned? Does anyone else want to answer that?
So something interesting I learned that is actually talks about what you just asked. It's actually easier for the Doppler to read a speed from the front than it is from the side, just based on the way, with the animation you saw, with the way the waves are changing, it's easier for it to get constant waves from the front that are like being compressed than it is for it to see from the side, just because of the way the waves are changing frequency as it moves across.
If we have one more question that says, what is the next thing you'd like to measure? When we were doing our experiments, this is for me personally, but when we were doing our experiments, lots of different shapes were giving us different signals. And we know that, certain stealth planes and those planes are designed so that radar signals bounce off of them. So something that I would like to see is how strong is the signal? How much can I pick up a ranging signal or a SAR signal from things that have different shapes? If it's a sphere versus just a screen versus maybe something triangular shaped, something like that.
Okay, so we have time for one more question, and then we'll move to the next group.
Let's see. My asks, what did you learn from this exercise? I think that's a good question to end it on.
And Sujay and Hayden, be quiet. Let somebody else in your group speak.
Well, throughout this whole experience in general, I definitely learned like how to persevere through all my fails and all my errors. Because when I first started using the radar, I had no clue how to interpret the graphs. I had no clue how to zoom in on anything. I was reading it, I had no clue what I was reading. But then through trial and error, through cooperating with each other and through bouncing ideas off each other, we just learned how to work through those problems, and we learned how to view our data in the best way, just for us to get the best possible data to present to you guys.
Yeah, so before I started this program, I had no interactions with radar at all. But over the course of this program, I learned many applications of the radar. And then we kind of messed around with the settings a lot when we're kind of gathering data, because sometimes if let's say the bandwidth, if it's too small, it wouldn't get the data that's necessary for objects that are far away. So we kind of had to mess with the settings a bit to get the data that looks the best. Yeah.
Yeah, definitely. About the settings, at first we just sort of did what the instructors told us to, but then as we did more experiments, we sort of got our own feel for what the settings did to our data. And then over time, we just sort of developed an instinctual sense for if we want to make our signal stronger, this is what we should do. If we want to get clearer data with better resolution, this is what we should do. And I just think that was super cool for me to just have that skill learned without even, someone, expressly explaining for each experiment this is what you should do, but just through trial and error. I think that was a really cool experience for me to learn that way.
I thought
Okay.
it was also, oh, sorry.
No, go ahead. No.
Yeah, I thought just it was great to learn what kind of difficulties we would encounter, and also related to how we would use the radar in the real world. We learned in one of the lectures about how radars could be used in search and rescue parties. And in our experiments, we saw the types of outside factors that would impact what the radar would pick up.
Okay, thank you so much. I see the comments in the chat. They did a great job. And some of the questions that are asked that have not been answered will probably be answered in some of the other presentations. So just hold tight.